All right, so we're going to start Unit 5 with this lesson. So I am doing the topics out of order. I feel like it just works better for us to do the extreme value theorem first, and then we'll go back and do the mean value theorem. It doesn't really matter which order we do it in. So anyway, before I have you guys do the next two tables on your own, let's talk about what some words mean. So a critical number is something you're going to hear a lot for a while. And a critical number is a value C, comma, for which f prime of C equals 0 or f prime of C is undefined. So the derivative is 0 when you plug C in, or the derivative is undefined when you plug C in. Okay. Relative extrema is what we're going to talk about, actually, in absolute extrema. So we're talking about maximum and minimum values here. So the relative extrema are the maximum values that they're higher than the ones that are relative to it or close to it. And what we like to say about those is that they're points on the graph where the function changes from increasing to decreasing, or vice versa. What they look like on the graphs is the hills and the valleys, so the top of the mountains or the bottom of the valleys. And one thing to keep in mind about relative extrema is they occur at critical numbers. So those tops of the mountains or bottoms of the valleys is when the derivative is 0 if it's curvy, and then if it's pointy is where the derivative is undefined. And the last, the absolute extrema. We haven't talked about that a whole lot throughout your mathematical career, but they are the absolute highest and lowest points on the graph of the function. Okay, so what I want you guys to do is the table at the bottom of this page and then the table at the top of the next page. So go ahead and pause your video and do that. So you're looking for coordinates of relative extrema and coordinates of absolute extrema. And then on the second page, you have a restricted domain that you're doing the same thing. So go ahead and pause the video and do those, and then start it back up and we'll check your answers. All right, so here are the answers to the first one. So on this F graph, there is no absolute maximum because the arrows go up and up forever. But there is an absolute minimum because we don't ever go lower than this point right here. And then for the G graph, it has both absolute max and absolute min because it has endpoints. It doesn't keep, you don't have the arrows that keep going. And the domain of the function, did the absolute extrema occur at the relative extrema? Well, it did on F. The relative minimum in one of them ended up being your absolute minimum, but then on G, the relative maximum wasn't an absolute maximum. The absolute maximum was at an endpoint on that graph. All right, and then for this table, for the different boxes, you had different restricted domains, and you just found the absolute maximum within that domain. And so hopefully you found what I wanted you to, which is we want to know when the domain is restricted to a particular closed interval, what three places did the absolute extrema occur? So they occurred at the relative extrema, which was either where f prime of x was 0, so that was the rounded relative extrema, or where f prime of x is undefined, which was at the pointy edges. And then the last place is what people forget about, but don't forget about it, that those absolute extrema also occur at the endpoints of the interval. Okay, so don't forget about the endpoints. We always want to check those when we're looking for absolute extrema. So let's talk about the extreme value theorem, or the EVT. So the extreme value theorem states that if f of x is continuous on the closed interval from A to B. So that means you can't have a vertical asymptote at the A or B, you can't have a hole in the graph at A and B, and it has to be continuous all the way through the interval. Then f has at least one absolute minimum and at least one absolute maximum. So when you have closed interval, there's going to be the highest and lowest points on the graph, as long as the function is continuous within that interval. All right, so on number 1, we're going to use the extreme value theorem to locate the absolute extrema of the function. Okay, so this is where I like to talk about like a history test. So let's say that you are taking a history test and the teacher asks, who is the 3rd president of the United States? And you answer Monticello. If you were that history teacher, would you give the person any credit for that? I'm guessing you would say no. But they have the right idea, because the 3rd president of the United States was Thomas Jefferson, and that is Monticello is where he lived. But that wasn't the question that the teacher asked. So you need, when you're doing these extreme value theorems, you need to know, are they asking where the extreme values live, or are they asking what are the extreme values? So locate is it's a clue. So they're asking you to locate the absolute extrema. So they're asking, where do they live? And when they want where do they live, we're looking for the coordinates, or the ordered pairs, or the points. All right, so we're looking for those. And our function is f of x equals negative x cubed minus 6x squared minus 9x plus 2. And our interval is a closed interval from -4 to negative 1. So to be able to find your relative extrema, they can be where the function is equal to 0. The derivative is equal to 0 or undefined or at the endpoints. Now this is a polynomial function, and polynomial functions are always continuous. So the extreme value theorem is applicable. But what we need to do first is find the derivative. All right. And then from that, we want to find the critical numbers. And the critical numbers are when this derivative is equal to 0. All right, and just to kind of get going on this, I'm going to divide through by negative 3. And then factor it. So we are going to get two critical numbers, negative 3 and negative 1, and they both fall in that interval. So we're good with both of them. All right, so what we're going to do is we're going to list our candidates. We're going to hold an election for maximum and minimum. And we're going to list our candidates that could possibly win. And so those candidates are going to occur at the endpoints. And so the endpoints are at negative 4 and at negative 1. And then we also have our critical numbers where the derivative was 0, and that's at negative 3 and negative 1, which are already listed as an endpoint. All right, and then to hold the election, what we do is we plug those into the original. So we're going to find f of negative 4 and f of negative 3 and f of negative 1 by plugging them into the original function. All right, and then I already did this, so just to save time, these are the values you get. All right, so we are asked to locate the absolute extrema, which means we need to tell where they live. So our absolute maximum, we have to figure out who won the election for absolute maximum. And it looks like there's 2 winners. It's a tie. So we are going to have 2 absolute maximum values or points. One is at negative 4, 6, and the other is at negative 1, 6. Okay. All right, and then for absolute minimum, the winner of absolute minimum is this one right there, the point negative 3, 2. Now, if it just said, what is the absolute maximum, you would say 6 is the absolute maximum. Or if I said, what is the absolute minimum, you would say 2. That's like asking, who is the 3rd president? You would say Thomas Jefferson. But we're asked to locate them, so you're asked to tell where they live. I know, it's kind of confusing. I'm sorry. All right, this next box is a different interval. But we've already done the work in finding the critical numbers, but our candidates are going to change slightly. So our candidates are going to be the endpoints, x equals negative 4 and x equals 1. And then our critical numbers that fall in between those, which are from before we already figured out negative 3 and negative 1. All right. And then we've already done a lot of this work. We found f of negative 4. We found f of negative 3. And we found f of negative 1. Now we need to find f of 1. That's that can be done fairly easy by just adding the coefficients. And when we did that, we would get negative 14. So for this interval, we have different winners. For the absolute minimum, we have a different winner, but the absolute maximum is the same. So the new winner of absolute minimum is 1, negative 14. Okay, so let's look at number 2. Number 2 says, for each of the following functions, state specifically why the EVT is not applicable on the given interval. If it is. Why it is or is not, sorry. Okay, so we are going to do the last one together, and then the other two are going to be part of your assignment. All right, so we have a natural log function, and it's been a while since you guys have graphed a natural log function, but the domain is going to come from saying that the argument is greater than 0, or solving that, we would get that x is greater than negative 7. So this logarithmic function is going to have a vertical asymptote at negative 7, and it's going to curve up like something like that. Now, it's not perfect, but something like that. All right, and then our interval is from 5 to 0, negative 5 to 0. So negative 5 is right here. And then 0 obviously is right here. So it looks like we're in good shape from negative 5 to 0. There aren't any vertical asymptotes or holes in the graph there. So the function is continuous on that interval. So for our specific reason, what we would say is the EVT, or extreme value theorem, is applicable for f of x on the interval from negative 5 to 0, because f of x is continuous for all x is greater than negative 7, which includes the interval from negative 5 to 0. Now, if our interval had been from negative 8 to 0, or even negative 7 to 0, we would say no, that it would not be applicable. Okay, we are going to do one more together, and it's going to be number 4 on the back page. So on the directions for the back page, we're given the functions below. Determine the absolute extreme values of the function on the given interval, and provided the extreme value theorem is applicable. If it's not, state specifically why it is not. Okay, so we have to think about, are they asking us who the third president is, or are they asking us where he lives? So if it's asking us the absolute extreme values, they're asking us what it is, who it is. So we're just giving the y values here, not where it lives, what it is, who it is. Okay. All right. So on number 4, we have g of x equals sine of x squared plus cosine of x. Now, sine and cosine are continuous everywhere. So sine squared would also be continuous everywhere. And then when you add two continuous functions, you get a continuous function. So this is continuous. So it satisfies the condition of that. So what we need to do is find the derivative. Now this is not a super easy derivative to find. So when we find the derivative of sine squared of x, we have to do the chain rule. So on the chain rule, we start off with the square. So when you have the derivative of something squared, you multiply by that 2 and take 1 away from the power. But then we have to multiply by the derivative of that something. So the derivative of sine is cosine. All right, so that's the chain rule. So if that didn't make sense to you, I'll write it down up here. It's basically sine of x squared. All right, so you take care of the power rule first, and then you have to multiply by the derivative of the sine of x. All right, and then the derivative of sine of x is cosine of x. All right, so that is just this part. All right, and then we have plus, and then we have to find the derivative of cosine of x. And the derivative of cosine of x is negative sine of x. So I change that plus to a minus sine of x. All right. And then if we want to find our critical numbers, we want to find when this is equal to 0. Now, we could do this by hand, where we factor out a sine of x and then solve the two equations. But I'm just going to remind you how to do it in the calculator. Okay, so I'm just going to type this in. I'm going to make sure I'm in radian mode. I am. All right, and I'm going to go to my window. So my interval is from pi over 2, to 2 pi. Let's go by pi over 2. Let's go by pi over 4. That doesn't really matter. And then this, let's go from -5 to 5. And we'll just go by 1. Let's see what this looks like. There we go. All right, so it looks like we have, that endpoint might also be a critical number. I can't really tell, but it's fine because we're going to use it as a candidate anyway because it's the endpoint. So we're going to go ahead and calculate. I think I'm pretty sure that is going to be pi because we're going by pi over 4, but let's just make sure. Calculate a 0. And left side, right side. Yeah, that's pi. And then let's do another one. Okay, that's our other one. 5.236. Okay. So remember, we are going to hold an election for maximum and minimum. And so our candidates are going to come from our endpoints and our critical values. All right, and then we'll go back to the original function. Oops. and we'll plug in those values. Now be careful that you don't use the derivative function. Be careful that you use the original, not the derivative. So I already did this just to save time. And you can do it in your head, or you can do it in the calculator. It's up to you, this one. Okay, now let's make sure we answer the question that it's asking. And it didn't ask where do the absolute extrema live. It asked what are they. So the absolute maximum that this graph G gets to is the y value of 1.25. And the absolute lowest that this graph gets to is the y value of -1. Okay, so that's the extreme value theorem and using candidates to find the absolute maximum and minimum. Don't forget about those endpoints. So endpoints and critical numbers are going to give you those absolute max and minimum values. All right, so your assignment is to finish this packet. So just do all the blocks that we haven't done.